omega in RD a locally finite set. And then when you take the intersection with a box, lambda here will always be box. It will stand for box. So we look at the finite box, and we take omega lambda at the intersection. So here's a picture. And then we're interested in the set of permutations or bijections from the points in this box, which are finitely many, to themselves. And we will put some weights on these permutations, which depend on the geometry of the points, so that essentially they will be proportional to the exponential of minus alpha. Minus alpha will be a parameter. And then we take the square displacement of the point, so x minus sigma x squared. And the questions here, well, considering this model was motivated by, well, started back in '53 by Feynman, who wanted to study Bose-Einstein condensation, and then he got a representation like this via the Feynman-Cox formula. And it's also related to the interchange process. So if you don't know what the interchange process, it's very simple. You take a graph, then you put on each of the vertices of the graph, you put a particle, and you set an independent Poisson process, rate 1, say, on each of the vertices, and whenever a clock rings, you interchange the particles on the adjacent vertices, and you run these dynamics for a finite time, t. And when you finish, particles have moved, and they define a permutation, because, say, the particle which started at x now is at position y, the particle at y is at position z, and so on. So this defines a permutation, and if you think that the particles are doing random walks, then you can believe or convince yourself that essentially you might have a displacement like this, Gaussian type of displacement. And both for this model we are considering here, or for the interchange process, the goal, well, first of all, for this particular model, we want to see whether we can find an infinite volume limit when the box goes to infinity. But the main question relates to the geometry of the cycles. So you have a permutation, you decompose this permutation in cycles, and you want to know whether these cycles are finite or infinite, or whether you have infinite cycles, actually. So that's the problem. Now, in order to state our result, we need a little bit of formalism. So let me remind you about Gibbs measures. You have a Hamiltonian. For us, it's this. It's the sum of the square displacements. Then we have to consider some boundary conditions. And the boundary conditions here, just look at the box, then forget about the math. So what you do is you choose some permutation on the whole space, and this permutation will be C here. And then you consider the intersection with the box, with your finite box, of any cycle which is coming from outside the box. And the points taken by this cycle coming from outside will be forbidden for your distribution inside the box. So you can sample any distribution of any permutation inside the box, but you cannot use the points which are taken by the cycle coming from outside. In this case, it's just one cycle. You could have several. So this will be the boundary conditions. And then with the boundary conditions on the Hamiltonian, we define a set of measures which are well-defined on finite boxes, which are called specifications. So you just take the weights we had before, e to the minus alpha, alpha your fixed parameter times the Hamiltonian, which was the sum of the square displacements. Then you only consider permutations which respect this boundary condition. So this is a compatibility condition. And then you take a normalization. So we have these measures. And the goal is, the first goal is to find limits for these specifications when the size of the box goes to infinity. So we say that mu is a Gibbs measure if whenever you choose a box and a boundary condition, then when you condition on this boundary condition happening outside the box, what you get is the specification. And turns out, this very useful fact, that if you take your set of specifications, which are very well-defined measures, and you can take weak limits, whatever you arrive at has to be a Gibbs measure. So it satisfies this for free, this condition. So OK, now that we have all this, let us see what is known for the problem. Or, well, a brief review, not all, but mostly, or the main highlights. So the first result was by Gandolfo, Ruiz, and Woolsey in '07. And they proved that under some condition on the alpha, on the choice of alpha, namely that this quantity be less than 1, then there exists a weak limit for the specification. So as we saw before, this would be a Gibbs measure. And then this weak limit would assign if alpha is large enough, satisfying this, then the probability that there is a cycle of infinite length is 0. Here it's just stated for the cycle of the origin, but, well, okay, you can easily see that this means that there are no infinitely long cycles. The next result was in 15 by Biskup and Richthammer, and they really settled the full picture for d equal to 1. So the previous result was in the square lattice. So your choice of points was the integers in ZD. For d equal to 1, actually, they could take any point process under some conditions that there was no condensation. Yeah? No, they don't prove uniqueness. They just prove that there are weak limits supported on permutations with finite cycles. So going back to this result, they can take any any point process in R. And of course, there is some condition that you don't have condensation of points, because having condensation of points immediately will give you very long cycles because, okay, it's very cheap for a long permutation to make the jumps. So it's reasonable to assume that your points do not condensate, that they have some, they do not do that. And alpha can be any positive parameter. Then they show that there is existence and uniqueness of Gibbs measures, and they also prove that all cycles are finite here. And the methods are very one-dimensional. Essentially, they show, I mean, the crucial fact they show is that you can, with probability 1, you can find pieces of R above which there are no crossings. So there is no cycle going above these pieces. And with this, then the rest of it follows quite simply. And then also with Pablo Groisman and Florencia Leonardi, in 15, we essentially showed what you just asked. We proved that there is uniqueness of Gibbs measures with finite cycles. And we could extend the result. Actually, we had a condition. This condition was slightly stronger than that one. And under this condition, or a related condition, we could extend these results to a more general type of potential. So not just square displacements, but we could go to more general potentials. And the next result, so actually it's previous result, but it's interesting in what it says, was an annealed result, which was studied by, which was settled by Betts and Ulshi in 01. And they proved that for dimensions larger than or equal to 3, if you take your set of points as a Poisson point process, and this is an annealed result, meaning that they are sampling together the points. Say your reference measure here is Lebesgue, and you're sampling the points and the permutation you're sampling with reference measure, which is just the uniform measure on permutations. So if you take both of them simultaneously, then there exists a critical density depending on the parameter alpha, so that the density here, well, it doesn't show anywhere. The density here is just the density n over the size of the box. This is the number of points divided by the size of the box. And if this density is larger than some critical density rho c, then they can show that the expected fraction of points, not in infinite cycles really, but in cycles having size proportional to the total number of points, so proportional to n, nothing is infinite here. So the expected fraction of points which have length comparable to the total number of points will converge to this number here. So this means in particular that there will be very long cycles growing as a macroscopic fraction of the points in the system. Moreover, they can show that these long cycles, among other reasons, this says that there's not only one infinite cycle, but that there are several. I mean, not only one very long cycle, but several long cycles. So what this says is that if you take your long cycles, you order them in decreasing length, and you rescale by n times rho c, you have to do some rescaling, then this converges to the Poisson-Dirichlet distribution. And it doesn't matter what this distribution is, but the main point is that this is the same thing you find when you study uniform permutations. This is a well-known result for uniform permutations. So this is saying that, okay, in this regime, we're seeing the same thing as we would from uniform permutations. And this is really the behavior that is expected in general. So what is expected is that for d larger than or equal to 3, this is really what we should be seeing. The problem with this result, though, is that this is an annealed result. So points and cycles are being simultaneously sampled. So, and the techniques do not let us determine how the points are being distributed. So you could actually get a very long cycle by choosing points which are very close together. And then getting a very long cycle would cost you nothing. So really what we want is not this kind of annealed result, but a quenched result, something that says sample the points and then determine what the cycles look like on your set of points. If you're sampling them simultaneously, you could be hiding the information about the cycles just by choosing points which are very conveniently concentrating. What am I doing? Okay. How much time? 2 minutes. Okay, so let me just say what our result is. So we do this. We take a Poisson point process on our D, and I'll just skip this part. And once we take this Poisson point process with a certain density, which unfortunately we have to take less than 1/2. This is technical, and actually the density and the parameter alpha should scale together. We shouldn't have to put conditions on both simultaneously, but we have some combinatorial estimates, and this comes out. Then we can show a large temperature result. So we can show that for alpha larger than or equal to alpha star, well, for those of you familiar with statistical mechanics, here alpha is not the inverse temperature, but the temperature. So this is for alpha large. Then we can show that for almost every realization of your Poisson point process, then there exists a Gibbs measure. So first of all, we have Gibbs measures. And not only that, but it is a unique Gibbs measure with the property that it is concentrated on finite cycle permutations. So, and we obtain it using this fact I mentioned before, that this is just a weak limit of the specifications. So this would say that for alpha large enough, okay, cycles are all finite. With probability 1 for any realization of your point process, and alpha is the same. It doesn't depend. It's not a random number depending on theta. So I think I have no time for the proof. I should just say that this alpha star here is not optimal at all. This is not a critical value. It's a value we get because of our techniques. And that if anyone in the audience has any idea about percolation techniques or anything that could help us actually treat the low temperature case, which is the interesting one, the interesting problem here is not alpha larger than alpha star, it's not the large temperature, but the small temperature would really be happy. It would be very happy if you could help us determine what happens when there is condensation. So let me just say a word about the proof. The crucial result, the crucial technique is a coupling method. So we set two types of dynamics. One of them is dynamics with exclusion. So we add and subtract and remove cycles, but we have to add new cycles that are somehow consistent with what we have in the sense that they don't use the same points. And then we show that with these dynamics, the specifications are the invariant measures. And we then compare these dynamics with another one where we just keep adding cycles according to some rates, omega lambda here, where omega lambda are these weights we saw before. And we remove them at rate 1. And now here, this is just a birth and a huge collection, 1 per cycle of birth and death chains. And of course, they have, we know the invariant measures. They are just the product of independent Poisson random variables. And then we compare these two dynamics. On the one hand, there are no restrictions. On the other one, we have some exclusion restrictions. And we can show that there is some domination like this. The free process dominates the process with restrictions. But we have good control on this invariant measure, much better than this one. So we can do a lot of estimates. And essentially, using this, we can prove tightness. And from here, existence. And then we can prove uniqueness. But I think I'll stop here. So somewhere.
So unfortunately, we don't have much time. Well, maybe one quick question.
Do you expect that at low temperatures?
At low temperatures, you expect to have the same result. So you have, for D larger than or equal to 3. For d equal 2, it is expected that there will be the mean cycle length will blow up, but that cycles will still be finite with probability 1. For d